The mid-1980s automotive industry operated with a sprawling industrial footprint. It was a global manufacturing engine built entirely around the mass production of heavy steel and combustion. Engineers spent their careers perfecting the physical machine. They focused capital on shaving millimeters off cylinder walls, optimizing fuel injection ratios, and improving structural aerodynamics. Innovation meant physical survivability. The bleeding edge of automotive safety was a bag of air, physically triggered by a mechanical accelerometer. Even when automakers introduced advanced electronics, they meant complex digital dashboards. Screens displayed maps or speed. They were passive hardware devices, requiring constant human input. Every single manufacturer operated on the exact same premise. A car was an inanimate tool, and it required a human mind to operate it at all times. Because the entire corporate structure was optimized to bend and move metal, the industry possessed a structural organizational blind spot regarding software and artificial intelligence. The breakthrough happened outside the traditional auto hubs, at the Bundeswehr University in Munich. There, an aerospace engineer named Ernst Dickmanns began asking a completely different question. He bypassed the industry's traditional chassis optimization to focus entirely on perception, teaching a machine to accurately interpret its real-world surroundings. His project, VaMoRs, used a modified Mercedes-Benz van. To be clear, it relied on no hidden rails, no buried magnetic tracks, and zero remote control. Dickmanns engineered a vision-first philosophy. The system identified road markings, translating raw pixels directly into steering and throttle commands. Onboard computers processed this instantly. As the wheel turned, the camera's perspective updated, creating a continuous autonomous cycle. Dickmanns successfully transitioned the car into a computational agent capable of interpreting its environment. Taking a computer out of the lab and placing it into the chaotic environments of real European roadways presented an extreme engineering challenge. By 1987, the 5-ton VaMoRs van was successfully driving autonomously on closed highways at speeds up to 96 kilometers per hour. The system scaled rapidly. By the mid-1990s, Dickmanns loaded his next-generation software into a sedan named VaMP and sent it on a 1,600-kilometer endurance test. This map tracks that specific journey. The software navigated the heavily trafficked motorway from Paris all the way to Munich. Along the route, the system executed complex passing maneuvers and maintained sustained peaks of 130 kilometers per hour with minimal human intervention. The successful completion of the Munich-Paris route proved that AI could control a multi-ton vehicle at highway speeds in real-world conditions. Yet, outside of that single experimental lane, the human-driven reality of consumer transit remained entirely static. Despite undeniable proof of a working autonomous vehicle, the global automotive giants effectively ignored Dickmanns' work. Their supply chains and workforces were built to assemble mechanical components. They had zero structural capacity to absorb and deploy millions of lines of code. Beyond the assembly line, executive leadership lacked the vision for the technology. The idea that a vehicle's value could be defined by code rather than internal combustion was an alien concept. A technological milestone holds no weight if the dominant industry is structurally unprepared to commercialize it. It would take decades for the rest of the world to catch up to what happened in Munich. Leading modern companies, most notably Tesla, eventually discarded expensive LiDAR sensors to embrace the exact vision-first philosophy that Dickmanns pioneered. A full 30 years stand between that heavy Mercedes van steering itself and the commercial deployment of modern advanced driver assistance systems. Ernst Dickmanns is the unheralded engineer who proved that self-driving cars were a solvable problem rather than science fiction. He proved machine intelligence could navigate the physical world, but that intelligence remained locked in a lab while the industry kept building mechanical boxes. What will it take for the automotive machine to finally realize it needs a brain?